Thank you. Hi, everyone. My name is Hideki Koike, and I'm from Tokyo Institute of Technology. And recently, Tokyo Tech has changed its name to Institute of Science Tokyo, by the way. So today, I'd like to talk about SolePoser, real-time 3D human pose estimation using Insole pressure sensors. This is a joint research project between Tokyo Tech and CMU. And unfortunately, the first author of this paper, Arwin, could not attend UIST, so that's why I'm here. So as you may know, there are many motion capture systems, and they are divided into two types, the optical system and the inertial system. The optical mocap system requires the optical motion capture system requires many cameras and complicated setups. The user can only move in the camera-equipped mocap room, which is physically limited in size. The inertial mocap system requires the user to attach many IMU sensors on the body. Wearing the mocap suits or attaching many IMUs on the body is time-consuming and tedious. Much worse, these systems are very expensive. So on the other hand, the current computer vision technologies enable to estimate the 3D human pose using a single RGB camera. However, these methods is less accurate in the wild because of the lighting conditions, resolutions of the image, etc. So the motivation of this research is to develop the mocap system which needs simple setup, data-driven, robust, affordable, and not vision-based. So I'd like to talk about some related work. So one approach is sparse IMU-based pose estimation. For example, IMU poser uses 2 or 3 IMUs from daily devices such as phones, watches, and earbuds to facilitate everyday pose tracking. However, lower body and global transform is less accurate. Another approach is to use the pressure sensor on the floor. Ground link and Intel carpet estimates users' pose using the pressure data measured by the pressure sensors on the floor. Although the lower body and global position is accurate, it requires the carpet-like devices on the floor. And this slide shows an overview of the SolePoser. We use a pair of Insole sensors capable of streaming real-time 16-channel pressure data and 6 degrees of freedom IMU data of both feet via Bluetooth. The data is processed by our SolePoser network and produce the 17 joint position as an output in real time. To the best of our knowledge, our work is the first that focuses on learning 3D human full body posture from foot dynamics. Since there is very few data set, which includes pressure data and 3D pose data, we first started to collect data set. We developed 2 different 3D motion capture data sets, SolePose Sports and SolePose Exercise. The SolePose Sports dataset focuses on activities where foot movement is crucial and conventional mocap system typically fall short. The dataset incorporates dynamic sports activities such as skiing, snowboarding, golf swing, and table tennis. The SolePose Exercise dataset includes typical daily exercise activities such as walking, jogging, squatting, and jumping. For more details of the datasets, please refer to our paper. This slide illustrates the architecture of the SolePoser network. The SolePoser consists of several key components: an initial feature extraction module, a transformer network for spatial temporal feature extraction, a cycle consistency feedback, network in here and here. A simple MLP is used for IMU stream, and a graph neural network is used for the pressure stream due to the sparse input shape of the pressure data. To train our transformer model, we designed a specialized loss function that incorporates human pose losses and a double cycle consistency loss. For the pose losses, we minimize the error between the predicted and ground truth pose by using a combination of 2D and 3D pose losses. So this is a real-time 3D body pose estimation using the insoles. As you can see here, the lower body and upper body, except for the arms, are precisely captured, estimated. But as you can see here, the arm part is not recognized because it is very difficult to estimate the arm pose just by using the foot pressures. I will describe it about later. We compared SolePoser to several baselines, including some state-of-the-art across 3 datasets, considering inference time and performance. Since there are no previous work focusing on foot pressure to body pose regression, we included 2 real-time sorter methods for sparse IMU and an RGB video-based estimation as a reference. As shown in this table, we evaluate performance in 2 settings, one excluding the elbow and wrist, and the other including them. The metrics used are the 3D mean per joint position error, MPJPE, in millimeter, and mean per joint angle error, MPJAE, in degree. SolePoser surpasses the vision-based method PoseFormer and PressNet in speed. For accuracy, SolePoser consistently outperforms the baselines. In the 17-joint setup, due to the lack of hand and arm information, almost all methods experienced a significant performance drop, while the decrease of the SolePoser remains the smallest. This slide shows the result of ablation study. We begin with a single transformer network where the input sequence of IMU and pressure are concatenated and flattened to a single vector. Comparing the first 2 rows in the table, it is evident that even without specialized feature extraction, introducing foot pressure data into the model can improve pose estimation up approximately 17 millimeter and 8 degrees. The introduction of cross-attention, our full system SolePoser results in an improvement in MPJPE for the SPS dataset, but does not affect the MPJPE for the SPE dataset. For the MPJAE, it improves for the SPS dataset, but slightly worsens for the SPE dataset. To demonstrate the practical effectiveness and robustness of our system, we conducted real-world tests involving alpine skiing and walking in natural environments. Ground truth data were captured using X-Sense suits, which are wearable mocap system featuring 17 wireless IMUs. The results are shown in the table, and the qualitative results is shown on the right. As you can see, PoseFormer, which is representative CV computer vision-based method, fails to estimate the lower legs and spine. So estimating arm and hand position from foot pressure data is less reliable. The integration with wrist-worn IMU devices, such as smartwatches, is a potential solution. Another limitation is body shape estimation. Although we normalize the height and weight with the insole values, the bone length information is not incorporated. Adding a self-calibration phase would not be difficult. So here is the conclusion of my talk. So I would like to emphasize that our system is applicable not only to sports analysis, but also to rehabilitation exercises. Currently, rehabilitation patients have to go to the hospital and capture their gait data in a special room with motion capture systems. Walking pose in such special room might not reflect their normal walking pose. Using our technology, the patients can capture their walking pose in their daily activities. So thank you very much for your attention, and please come to the poster session for detailed discussion. And also, in addition, as you may know, the next CHI conference will be held in Yokohama, and Yokohama is very close to our campus. So if you are interested in trying this ski simulator, you are very welcome. Thank you very much.
Questions from the audience, please just queue up there and then ask your question.
Hello.
Hi.
Thank you for the great work. My question is about the actual case of the usage in, for example, the ski. So probably the pressure from the shoes or boots will probably affect some kind of disturbance or kind of the affect the accuracy. Do you have any idea about that?
Well, we didn't see such. We didn't see that because we have collected the data by putting the insoles inside the ski boots, and so all the data set collected in our SolePoser S dataset is captured by the insole sensors inside the ski boots. So I don't think that there is no problem about that.
Okay, let's thank our speaker again.
Thank you very much.